In fractional version, we have just in one loop just this logarithm to a positive power. In fact, means that we can obtain here answers also not only for integer values as in APT, but also for fractional indices. But I will not discuss more about fact here. I will concentrate on APT. So my last item here in APT subject about how to resum series here. If we take into account this quantity and suggest that coefficients dn depend on some generated by some generation function with this property that this notation, and that means that coefficients dn are just moments of some integration variable t with weight function p, generating function. So we put it here inside, and what we need to sum up this series. How to do it? We just rewrite it in different indices, shift by 1, and then use this relation. You see what you have here. Instead of this guy here, you have unity of n factorial. Then you have some power operator, and then this object is some derivative, n derivative of this object, and it multiplied by some power of t. Do anybody knows what it is? Do you know so-called power series for how it names? So I mean Maclaurin formula. Who knows it? What is Maclaurin formula? How you put your function f(x) to Taylor series? What is it? It is f of 0, yes, x ante n factorial. It's just what we have here. So here we have Taylor expansion. In fact, we have Taylor expansion, but supplemented by some averaging with some generating function of our coefficient. So the result is very simple. But it is just this over this averaging over generating function of object, which is like here, it is argument L and shifted by T. So this is just what analytic perturbation theory dictates for summation of the whole series, but only if you know this generating function. It is an impossible task to calculate something completely to all orders, but suggest we have it. And also the same formula holds for Minkowski region. The only difference, instead of Euclidean coupling, you should use Minkowski coupling. The same can be done for global case, which you take when you take into account quark threshold, but I will not concentrate it with some technicalities which are not so important. Now let us speak about what we have for this in his approach for Higgs boson decay into B anti-B pair. It is related with correlator of two scalar currents, and this is the relation for with decay with this RS for case of scalar current correlator. We have here some running of mass. For this reason, we have not exactly unity term, but with some exponent. So our starting point not from unity, but from this exponent of coupling. And in case of APT, so-called F-APT, fractional APT, we have analog of this expression, and we can resum it if we produce a model for this generating function of our perturbation coefficients. And there is results for perturbative QCD expressions for first coefficients. D1 is normalized to unity automatically, D2 is 7, D3 is 62. We suggested this model by hand, which is created by by gluing Lipatov asymptotics with gamma function with power law. And we take into account also subleading Lipatov asymptotic, but it can be different. But for these very reasonable numbers, we have very good quality because it is just fit one-to-one. Two numbers by two parameters completely fit it is just nothing. But if we take into account this model and produce our prediction for next coefficient, it is 662. And calculation quite recently in 2006 was done, and it is 620. So our model is good. Now if we take into account these three numbers and produce in this type of model another fit, then numbers a little bit changed, but the order is the same approximately. So the parameters are changed slightly. So we think that this model is quite good for these numbers. And our prediction for D5, which is not calculated and which takes, I don't know how many thousands of diagrams to calculate and how many years, it is 7,008 numbers and something. So it is huge numbers, but very interesting result that if we define relative errors of series truncation at nth term with respect to the whole summation, which we know by our formula, the result is at a two loop. This is, I take into account only two coefficients. We have approximately 2%, 2.5%. Very good, how to say, accuracy. If we take into account the third coefficient, about 1%. If we take into account the fourth, which can be calculated by Chetirkin, it will be 0.5%. But if we are thinking about calculating the next coefficient, D5, then if we take it into account a la our model, the price will be just, instead of 0.5%, we will have 1/4%. So in order to reach this accuracy, to spend so much time to calculate this contribution, from my point of view, it is not very useful task. So conclusion, then you see that taking into account four contributions, we have this accuracy. If we take into account fifth correction, it will be only 0.3. The same thing can be done for the case of Adler functions, so I just completely list all these things because it's complete analogy, also modeling. Also what we have now by this year calculation of Chetirkin group, it is VI prediction. What we have from our model here is like this, and if we take into account all coefficients, it will be a little bit closer, but the next one will be huge. So, and what we have as a result, very interesting, because here we have here not so high values of Q squared. In Higgs boson, it was around Higgs boson, it was about 200 GeV squared. But here it is quite reasonable, 20 GeV squared. It is, in deep inelastic, it is quite good measurable thing. And take into account the second contribution, the second coefficient, to obtain approximately 1 promille accuracy. If you go further, accuracy will increase. Will not increase, will diminish. Your error increase. So the second term is unbeatable. You should stop here because your series is asymptotic. It has factorial coefficients. It is divergent series. And for divergent asymptotic series, if you know that from some point coefficient starts, contribution starts to enhance, that means that you should stop here and not go further. And here, this effect is taken just in the second coefficient. Fourth is higher and fifth also. So this is our prediction and now conclusions. APT provides natural way to Minkowski region without any problems about pose because analytization is everywhere. Both APT and FAT produce finite result answers for perturbative quantities only if we know generating function. If we don't know, and it is the case because nobody knows for real QCD some exact answers for all coefficients of perturbation theory, then you should model it and understand what to do after that. And just doing like this in the case of Higgs boson decay, we see that at this order of accuracy we have at this order of truncation, taking into account three coefficients, we have order of accuracy of 1%. And for other function, 1 promille, even already at second, taking into account second coefficient. So the main conclusion of my talk is just don't calculate higher order corrections too much. Use instead analytic perturbation theory approach. That's it.
Thank you. Question, please.
Do you have some exactly solvable examples for like two-dimensional QCD or Ringer model where you can estimate the accuracy of the method of analytic perturbation theory?
I don't know such examples. If you